Hello everyone. Today we'll be talking about how we monitor zero-day exploit on cloud. First, let me introduce our team. I am Xu Yue, and here is my colleague Huang Xiaokun. We are the security engineers from Alibaba Cloud. In the past few years, we detected and blocked dozens of botnets for our users on cloud. In this talk, first we will introduce the major threat on Alibaba Cloud and the zero-day racing game between Botnet and us. Then, we will detail how to identify zero-day payloads from HTTP logs. We can get this done automatically. And finally, we will show you some real cases of zero-day monitoring. The first question is, why Botnet matters? For now, Alibaba Cloud is the largest cloud service provider in China and has the third largest share of the global cloud computing market. There are over 40% Chinese websites hosted on Alibaba Cloud, and more than 1 million customers use our cloud security services. To protect cloud user security, we block about 6 billion attacks every day. We see that most of the attacks are web application exploits come from botnet. Looking at the diagram on the left, it shows the top 5 reasons of invasions on cloud. We can tell that web attacks is the major threat. The diagram on the right shows the vulnerability distribution of server-side web attacks. We can see that most of the attacks use public CVE vulnerability exploits. Some attacks are from scanner, and there's still a part of damage caused by unknown payloads, maybe 0 days. From the defender vision, those 0 days are the most troublesome. Every year, a large number of web vulnerabilities are published, including Java deserialization vulnerabilities and Web Framework RCE. For example, Struts, Drupal, WordPress. These critical vulnerabilities start a zero-day racing game between botnet and us. If we can get the zero-day payload first, then we can block it to keep our customers safe. Otherwise, the botnet may take down a large part of services on cloud. The right diagram shows how botnets spread with 0 days. At first, when a 0 day appears, only a small group of people knows the detail. Then, days or months later, the proof of concept or exploit may be released by someone on Twitter or GitHub, and it will be quickly integrated into the botnet to spread in a few hours. So, as a cloud service provider, our target is to get the exploit before botnet does and block the attack for our user. Here is our zero-day monitoring pipeline. First, we collect both network traffic and endpoint logs in real web applications. Then we produce a data mining model to separate the suspicious attack payload from the massive HTTP flow. Next, we use another algorithm to filter out existing end-day payloads in our exploit database, and the rest will be sent to a security expert to confirm if it's 0 day and evaluate its damage to the cloud. The most difficult thing is digging 0 day automatically from massive HTTP logs. Let my partner Huang explain how we get this done.
So our first problem is how to capture the real attack payload from massive HTTP logs. Since our goal is zero-day vulnerabilities, we cannot get any details in advance. So the common rule-based traffic matching method is invalid. Besides, the PB-level traffic on Alibaba Cloud also requires us to establish an integrated, universal, automatic, and low false positive detection mechanism. Here, we share our thoughts and practices. We rethink what is a service-side web attack and what it can be abstracted into. It can be summarized as malicious data travels through the trusted boundary and reaches system service. Here, the malicious data refers to the HTTP data containing the attack payload, and the trusted boundary means web application. Finally, system service can refer to any abnormal behavior of the system. The whole process is shown in the figure. We use the taint tracking method to monitor the data flow. We mark the key data carried in the HTTP log as taint. Then this tainted data flow in web applications or middlewares. Finally, it becomes a part of the abnormal behavior alarms of the system. And now, we have established a correlation between traffic data and terminal alarms. So, we can infer that this HTTP record contains a suspicious attack payload. Here is an example. The RCE vulnerability via velocity in Apache Solr last year. We can see in the HTTP log on the left that the attacker execute a malicious command and download and execute a bash script. The HTTP data is processed by the web service and finally executed by the system. We can see the same part in the HTTP log and process startup log. In this way, if we can automatically correlate traffic data with terminal logs and find similar paths, we can identify attack traffic. Here, we introduce how to find similar paths, and we call it n-gram payload matching. First, we iterate each HTTP request and use rule-based methods to split words. Then, we use 2-gram to generate feature patterns. We use these generated feature patterns to represent the information in the original data packet, and we call it pattern. Then, we do the same to generate feature patterns from system log. Finally, we compare two patterns. If they are highly similar, we consider this HTTP request to be a suspicious attack payload. For example, there is a command injection vulnerability that exists in the time processing module of a well-known CMOS. The attacker used this vulnerability to load and execute a remote file and tried to use a JPEG extension to bypass the intrusion detection system. The content on the left is the original HTTP request we captured, and it didn't hint any rules we know. We extract its core data and generate feature patterns through the 2-gram algorithm, and do the same for the process log. You can see that the two patterns are highly similar, and the similar paths are indicated in blue. Therefore, we have determined that this HTTP request is an attack payload.
Okay. The former example shows the data flow tracking method works fine with RCE attacks, and it can also catch other web exploits such as SQL injection, XML external entity, web shell upload and connect, and directory traversal. Now let me show you more cases. File upload is another common web vulnerability. By abusing some web application features, attacker can upload malicious scripts to take over the web server. For example, some web application APIs are designed to upload image, but hackers use it to upload PHP files, then connect it to execute malicious command. This example is a file upload zero-day vulnerability of a well-known but we cannot tell OA system. We caught it several months ago. In these logs, we can see that the string in red is a file name, which occurs both in HTTP log and endpoint file log. It means someone wrote a PHP file successfully into the web server, so we can use data flow tracking method to dig malicious HTTP payload automatically. Here is another example about directory traversal vulnerability. In this case, we gathered both HTTP request and response. Then we matched file path in request and the file body in response. We combine both signatures in data model and filter out the malicious HTTP request. With this method, we capture several zero-day exploits of Citrix and F5. Now, let's go through a real botnet defense story. In early 2019, a botnet called Imposter Miner used Jenkins RCE zero-day to spread and infected thousands of Jenkins web servers. 20 days before that, we had captured the zero-day payload, so our cloud users are well protected. Let's dive into the RCE attack payload. We can see the strings in red contain some information. There is an HTTP URL and some special strings like tw.orange, POC, and a number 8. These strings can be matched to a remote download behavior captured by endpoint agent inside server. In this case, our Ngram payload matching algorithm called this Jenkins RCE automatically, and we analyzed it at first time. Then we confirm that's a zero-day. Here is the timeline of Imposter Miner botnet with Jenkins RCE. In December 2018, the security researcher Orange posted a short message in Twitter, said he had found a Jenkins RCE, but no vulnerability details were published. Then, at January, Jenkins officially claimed 3 CVE vulnerabilities, but the details were still unknown. Later, at the 13th of January, our zero-day monitoring captured the first exploitation with complete attack payload. 2 weeks later, the proof of concept script was released. Then Imposter Miner botnet started to spread with this vulnerability on February. In this case, you can see that we won the zero-day racing game about 20 days. We updated our defense rules before botnet spread, and most of Jenkins web servers on Alibaba Cloud were well protected. The former example shows that how data flow tracking method helps us to catch zero-day payload. But that's not enough, because sometimes the payload is encoded or encrypted, and there was no string pattern available to match different logs. Let me show you an example. This is the exploit of WebLogic RCE. As you can see in the red picture, Those malicious codes was encoded in bat array and separated by XML tags. By combining those bat and translated into string format, you will get a malicious command. The question is, when the 0-day comes, no one knows how it works. Looking at the HTTP post data, even experts cannot tell if it's malicious or not. For this encoded 0-day exploits, we will use some statistical methods to help. Our assumption is that botnet and normal users act differently on cloud. When hackers or botnets use 0-day to spread, a group of servers will raise a same type of endpoint alert in a short period of time. Meanwhile, we observed that they were both connected to an IP or have similar network requests. Combining both sides, we can tell which group of requests are likely to be malicious. To achieve this, first we gathered HTTP request log and endpoint process log, then split word to each logs and searching the frequency item site. In this case, we can find a group of servers have three common strings from HTTP URI, the content length, and a special string in post data. On the other hand, these servers raise PowerShell alerts contain the same encoded string. That is a valid frequency item site. We can use it to identify which group of HTTP requests are malicious. This method helps us to capture WebLogic RCE before mistake botnet. This RCE 0-day has come to the eyes of the public on the 17th of April 2019, when China National Vulnerability Database published a warning without any vulnerability detail. 2 hours before that, we already caught this 0-day with the full exploit payload, which can be replayed. As you can see in the timeline, at first, only a few attackers used this 0-day to perform targeted attacks. Then, on the late April, a group of botnets started to spread this exploit, including the famous Mosaic botnet. This time, we won a half month's time to protect our cloud users against this vulnerability.
Due to the one-to-many attack feature of botnet attacks, our monitoring method does not depend on the specific content of the data. So it's also suitable for non-plain text attack payload traffic, such as encrypt backdoor connection, Java deserialization RCE, custom encoding method in HTTP request, and so on. The PHP study backdoor vulnerability used by the botnet in September last year is a typical example. The attackers send the same attack payload to multiple Alibaba cloud users. As shown on the left, the value in the accept charset field is the same. At the same time, in the terminal alarms of these attacked machines, they all have the same domain access and download malicious X files. So we can regard these two parts of data as a frequency item set. Within 30 minutes, this frequency item set appears on 160 machines. So we can confirm that it's a real attack payload. Besides, this method is also effective against common deserialization vulnerabilities. For example, there is a deserialization vulnerability in Apache Double. Attackers use twice to generate deserialization payloads and send them in batches to the same URL of the host on the Alibaba cloud. The picture on the left is the data packet we've captured, which contains the same deserialized data. Similarly, the endpoint alarm logs of these machines all have the same suspicious URL access behavior, and their parent processes are all Java. From this, we can construct a new frequency atom set to mark suspicious attack payload request. Furthermore, some special encoding method and combinations of utilization method can also be solved by this method. Same as before, we established the connection between the referrer data and endpoint alarms data by constructing the frequency atom set. When we get this frequency atom set data, it seems to be just a circle injection. So we did a manual analysis and found that its backend is a easy shop framework, a well-known open source model in China. There is a defect in the background implementation logic, and the purpose of RCE can be achieved by circle injection. In the end, let's make a summary of content of the whole topic. First, we introduce the background, the botnet with web attacks on cloud, the zero-day racing game, and the solution pipeline. The next two parts details monitoring methods and experience for plain text attack payload and encoded attack payload. In addition, our implementation needs to be automatic, efficient, because Botnet comes fast. That's all. Thanks for watching. You can contact us on email or Twitter if you have any questions.